So, in the previous lecture, we have discussed whether the features of the Schwarzschild black hole are generic. And historically, it was the central singularity, which apparently is something unphysical, that caused the most doubt. So, for a few decades after the introduction of the Schwarzschild solution, people believed that the central singularity of Schwarzschild is just a consequence of the spherical symmetry. And it took two things to change this viewpoint. So, first of all, it was the discovery of a second solution of the Kerr black hole, which is a rotating generalization of the Schwarzschild solution. And this solution also had the features of a horizon and a central singularity. So we will discuss the Kerr black hole later in this course. The second breaking point was the Penrose singularity theorem, proved in 1965, which have shown that central singularities are indeed generic in GR. What is even more important is that this Penrose singularity theorem doesn't explicitly use Einstein equations. So therefore, it's quite robust to the modifications of gravity in the presence of matter. And therefore, in general, it's a feature of many modified theories of gravity as well. And this tends us to believe that the real nature of the singularity, which of course is something apparently quite non-physical, can be revealed and solved only in the quantum regime, only in the quantum theory of gravity, which to this point does not exist yet. Good. So, in this lecture, we will cover the necessary preliminaries for the singularity theorem. And in particular, we will introduce the null hypersurfaces as the model, as the geometric construction that models a lot of features of the event horizon. Later in this course, a particular class of Null hypersurfaces, called Killing horizons, will be directly linked to a physical notion of event horizon of a black hole by the rigidity theorems. Good. So let us start. Let us start with the definition. So what is the null hypersurface? Well, the definition is simple, and it is simply a hypersurface, the normal to which is everywhere null. So, as we have just said, the main reason to consider null hypersurfaces is because they model event horizons. And the typical example would be, of course, the horizon of a Schwarzschild solution. So, let's consider Schwarzschild in the ingoing Eddington-Finkelstein coordinates. So we have Schwarzschild in V, R, theta, phi chat. And the horizon is simply a surface of constant R. R equals to M. So the normal is simply dr. So let us check that n squared is 0. So we have that so the inverse metric, G d mu d nu, is given by 2 dv dr plus 1 minus 2 mr dr squared plus 1 over r squared d theta squared plus 1 over r squared sine theta squared d phi squared. Well, checking this remains as an exercise. And therefore, n squared equals g mu nu and mu and nu equals g r equals 1 minus 2 mr, which of course means that the horizon is indeed a null hypersurface. The generator of this null hypersurface, that is the vector, that is the normal vector, is given by G that is d over dv. So now, let us note an important property of null hypersurfaces. So any tangent vector to a null hypersurface must be either space-like or null. So is either space-like or null. Well, this is easy to see. So if n is the normal to n, then x, being the tangent vector, must be orthogonal to n, so must be 0. From this, there follows two possibilities. So first of all, x is space-like. That is, lies outside of the light cone. Or, well, x is proportional to n itself. So these are the only two possibilities. So in particular, it means that n mu itself is tangent to the null hypersurface. So, in other words, the integral curves of the generator lie within the null hypersurface itself. So the integral curves of the null generator are not only lie within the null hypersurface, they are actually null geodesics. So let us prove this proposition. So the integral curves of n are null geodesics. They're also called the generators of n. And we say that n mu generates n, the null hypersurface. So the proof goes as follows. So first of all, let's say we have a null hypersurface, which, as any manifold, can be given by some algebraic condition. So f, the null hypersurface, is defined by f equals constant. In the case of Schwarzschild, it is the constant radius hypersurface. And so we have that df doesn't equal to 0 on n, and in other words, df is the normal, and generic normal looks like h times df, where h is arbitrary function. We want to prove that d and n is proportional to n itself. So we will, in other words, this is the geodesic equation. Okay, well, let's consider the left-hand side. So we have dn of n equals h times df rho 0 h d mu f, which then decomposes as h squared 0 f 0 t mu f plus zero f 0 h n mu. So this term is of course okay, because this term is proportional to n, so we don't need to do anything with it. And we now consider the first term only. So so note that for the scalars, note that since we're working with Levi-Civita connection, the covariant derivative acting on the scalar commute. So we have h squared 0 f d mu d rho f, which is the same as 1/2 of h squared d mu d rho f d rho f. Good. Good. However, now notice that this itself is the normal. That this itself is the normal. And therefore, since the hypersurface is null. So, in other words, the norm of the gradient of f equals to 0 on the null hypersurface. And since it equals 0, then we have that it means that it is killed by any direction tangential to the null hypersurface, and the only possible direction in which it can change is the direction normal to the null hypersurface. So, in the other words, it means that for any tangent x, this thing is 0. So the only way for the gradient of the norm of the normal to be non-zero would be if it is directed along the normal. So in other words, this is again proportional to n mu, which concludes the proof. So we have shown that the normal indeed generates the null geodesics. A good example is the Kruskal spacetime, where in terms of Kruskal coordinates, we can choose normal such as du, and any normal would look like h du, and of course n squared equals g u equals 0. Then we have the geodesic equation, equals, again, 1/2 of d mu n squared equals 0. So it turns out that for the Kruskal spacetime, the simplest possible normal is actually a good affine parameter for the null geodesics. If you take arbitrary normals of this form, then the term on the right-hand side appear, which means that the parameter we have taken is not affine. So, what is the affine parameter for the geodesics in the Kruskal case? So, we have that n mu, the generator, is minus r over 16m cubed to m d v mu, and therefore v is the affine parameter. Now we have found that the null generators of the null hypersurface are actually the geodesics. And by studying the evolution of these geodesics, in particular their deviation, we would be able to introduce a chart around the null hypersurface. So now let us do the first step in that direction. We would like to see how two geodesics deviate from each other. And let us start with the one-parameter family of the geodesics. So, what is the one-parameter family of the geodesics? Well, it means that we have a continuous family of curves. So, let's call it gamma, which depends on lambda and s. Yeah, so this is a continuous family of curves. And the parameter, where the parameter lambda is the parameter along the curve, and the parameter s numbers the curves. So lambda measures the distance along the curve, and this parameter numbers the curves. In other words, we have the geometry as where these are the geodesics, and we have surfaces of lambda equals constant, where this is the direction S mu equals T over Ts. And these are the geodesics, and they're given by S equals constant. And they're given by their tangent vector field U mu. So locally, this continuous family of curves can be seen as a two-dimensional hypersurface, as two-dimensional surface sigma. So as two-dimensional surface, and lambda and S are naturally the coordinates on it. So we have introduced U mu, that is tangent to geodesics, and S mu tangent to lines of constant S. So in this coordinate chart, in lambda S coordinates, U mu would then be given by d over d lambda, and S mu would then be given as d x mu. The S mu has the interpretation as the deviation vector, because if we consider the coordinates on two closed geodesics, so we'll have x mu of S lambda plus ds S mu plus, of course, higher terms. So this, therefore, has the interpretation of as the deviation vector. Yeah, so here, of course, we have taken gamma equals x mu of lambda S. I'm sorry, it should have been lambda and S in the opposite order here in the brackets. So, good. So we have U given by U d over d lambda, S is d over ds, and of course they commute as coordinate vectors. So we have U S equals 0 equals delta U of S mu minus delta S of U mu. Now we can derive an important geodesic deviation equation. So we can see how the geodesic deviation that the second derivative of the deviation vector along the null geodesics is actually directly connected to the curvature. So this is R mu lambda rho sigma u rho s sigma u lambda. We will now prove the statement. Good. So we want to prove that the second derivative of the deviation vector is directly connected to the curvature. So this is mu lambda rho sigma u rho s sigma u lambda. So let us recall or prove it, if you have never done this calculation, that one of the main, if not defining, properties of the Riemann tensor is the following relation. So if we are given three vectors, then the Riemann tensor, the curvature tensor is the commutator of two covariant derivatives. So u mu, v nu, and w lambda. We will take this property for granted. So the left-hand side, du s mu equals, since we have just shown that u and s commute, equals to du gs u mu. So equals, let's write it as a commutator, du ds u mu plus ds of du u mu. However, this is 0 since we're taking u to be a tangent vector to a finely parameterized geodesics. So as finally parameterized geodesics, and here, and for the first term, we use the formula. So this is nothing but mu lambda rho sigma, and we have u, s, and u again, rho sigma lambda. Good. So this, of course, is a linear PDE for the. This, of course, is a linear system of the PDEs for the deviation vector, and in differential geometry, we have a term for solutions of the such differential equation. So the deviation vector is also called the Jacobi vector field. So to this PDE is called Jacobi vector. Is called Jacobi field. the solutions along gamma. Now that we have nailed one-dimensional case, let us consider a more general case where we have larger parameter families. So now let us turn to a more geometrically interesting case where we have a more general family of the geodesics. So how we would like to see it? So we have some surface, and we would like that through each point of this surface there goes one unique geodesic. So this is called U in M, and these are the geodesics. So we will call this construction to be a geodesic congruence. Let's write a formal definition. So let U be an open subset of the manifold M. Then the geodesic congruence U is a family of geodesics such that through each point of U there passes exactly one geodesic of a family. So family of geodesics such that there is exactly one geodesic passes through each point P in M. So P in U. Good. Okay, so let us first consider the case where all geodesics are either space-like or time-like. The null case is a bit more complicated. So space or time-like, that is, we have U mu equals U squared equals to plus or minus 1, where again we can always take such an affine parameter, such a parameter that is first of all affine, and secondly it normalizes the tangent vector to be plus or minus 1. It is actually a good exercise to check it. It's actually a good exercise to check that we can always do this. So we can see it from the definition of the geodesics. As a parallelly transported curve, that is, as a curve that has the U of U proportional to U. Let's, for the better use, call the proportionality factor as alpha. So alpha some function, some smooth function. And then it is a good exercise to show that we can always find such transformation of the parameter lambda, where u mu is d over d mu, such that lambda is the affine parameter. Lambda is the affine parameter. Well, hint, we will have that d over d lambda of the logarithm of d lambda tilde d lambda equals alpha. So we will find lambda tilde from this ODE, and this ODE always has a solution. So therefore, such an affine parameter always exists. Furthermore, from the step, it follows that the affine it also follows that the affine parameter is not uniquely defined. It is actually defined up to two constants. So it is defined up to two constants. So the constant A would correspond to rescalings, and for space or time-like geodesics, we will use the freedom of A to we'll fix A such that the norm would be plus or minus 1, and B would correspond to the shift of the origin of the geodesic. For the null case, we have that u squared equals 0, and therefore there is more ambiguity in the definition of a affine parameter. The freedom is not fixed. So we have So now let us consider any one parameter family of geodesics. Consider any of geodesics in a congruence. So we have du of SA, which, as we have shown in the last section, commutes with u. And we can denote it as BABS, where BAB is GBUA. So note that BAB equals 0. Sorry. Note that BAB times UB equals to 0. Okay, so also note that the scalar product of U times S is constant along the geodesics of U. So we have U times du S plus S times du U which is of course equals to 0, equals to UA BAB SB equals to UA of the DA UB SB, and again it equals to GB U squared SA. And this is 0 SB. And this is of course 0 because U squared is constant. So this is 0. In other words, U times S is a constant along the geodesics. Any geodesic. Now we have one. Now, as we have just noted, we have two freedoms in the definition of the defined parameter, and we have fixed only one to set U squared equals plus or minus 1. We can now use the second freedom so that of shifting of the origin of the geodesics, so that U times S is actually 0. So, of course, we can do this on any given geodesic. And in general, this transformation would look like as following change, where on each geodesic we shift the defined parameter by a constant. It's just that this constant is itself geodesic dependent. So for each geodesic, so it differs from one geodesic to another one. So the remaining freedom of the affine parameterization. And of course, we will fix it such that U times S equals 0. So it is a good exercise to check that S times mu, that the new S times mu would transform as S mu plus dA ds u mu, dA ds u mu, and therefore we can always set U times S equals to U times S equals to U times S plus dA ds U squared. Now this thing equals to plus or minus 1. And in principle, this is constant on a geodesic. And since this is a constant itself, we can always pick such A. We can always pick such A such that U times S prime is 0. Since we have shown that u times s prime is zero everywhere is zero, and along the geodesic we have du u times s equals 0. Then, therefore, u times s is 0 everywhere. And not just on the open subset U. So, in other words, for an n-parameter family, we have defined the following geometry. We have defined the deviation vector and the tangent such that the geodesics crossing crossing our domain are orthogonal to our surface sigma. So where sigma has coordinates s, s prime, s double prime, and so on and so forth, and there is n of them. So we have therefore constructed a good, convenient coordinate chart, where the coordinate where we have one coordinate is given along the geodesics, and it is orthogonal to directions on sigma. And of course, we would like to extend such construction to the null case, because it is the null hypersurfaces that strongly resembles the horizon. For null geodesic congruences, the previous trick doesn't work, because u times s plus dA ds u squared is always 0. So the shifts of origin cannot fix as the u times s. Instead, we will do the following construction. So first of all, let's have sigma to be space-like. Space-like and intersect the geodesic ones. So that's sigma, and since we are given one null vector field, remember that in each light cone there are two null directions. So we can pick the second one. So we can pick the second null vector field, which is it's null, and squared equals 0. It is also belongs to the same light cone as u. So n times u equals -1. And then using it, we can extend and mu into the full space-time away from the sigma. By the parallel transport along u. In this case, we also immediately get that that n is null everywhere, and is null everywhere, and u times n is everywhere minus 1. So du times u times n equals 0. So in total, we have n squared equals 0, u times n equals minus 1 everywhere. Now, every possible vector can be decomposed into either one of the two light-like directions or the space-like direction. So every such vector S can be decomposed into plus beta n mu plus gamma s mu. So that's for any s mu. And we have u times s equals s times s hat equals 0 equals 0. And we can do this decomposition for any light go. In this case, S hat is space-like or null or 0. Yes. So note that u times s equals minus beta, which is constant, and u times n equals minus alpha. Okay, now let us consider the congruence, which contains the generators of the null hypersurface n. So consider congruence. Okay, so in this case, u mu is normal, and for any s mu tangent to null hypersurface, we therefore have u times s equals 0 equals beta, so beta equals 0. Now, it is convenient to write the remaining space-like part of the vector through the projection. So it is convenient to introduce the projection. So we have S mu equals P mu nu S nu, where P mu nu is the projection operator. It's delta mu nu plus n mu u nu plus u mu and nu. And the index here should be good. So this is the projection, and it satisfies the properties of the projection operator. That is, it squares to itself. And of course, P times U equals P times N. The action of the projection operator on U and N is 0. And P times S gives us S. Finally, it is a useful exercise to check that GUP equals 0. Well, I mean, we act with U. I mean, we act with the covariant derivative on the contraction, which is 0, or on N, or on U. If we act on U, it is 0 because U is a finely parameterized geodesic. And if we act on N, well, we already have the condition that N was extended by the parallel transport. So the du equals N. Good. Now, let us show that U times S equals 0. Okay, good. The proposition. So now we want to link the condition U times S, that is that S is tangent to null hypersurface, to its evolution. So to the evolution of its space-like part. So B mu S mu B mu, where B mu equals P B P. And as a reminder, B itself is given by d sigma U rho. Good. So, proof. Okay, so the action of covariant derivative on S mu equals to du minus nu equals to P mu, so we take the P out because it's invariant on the covariant derivative, P mu dus nu equals, in turn, P mu rho B rho C S sigma equals in turn to P mu rho B rho sigma B sigma lambda S lambda. Where this is the B hat, and we can also introduce, and this is the S hat. And recall that P squared equals P. So this concludes the proof. Good. Yes, on this step we were using the properties derived for B, derived for B. So this shows us that the evolution of the space-like part of any tangential vector is effectively governed by some matrix B mu nu. So we would definitely like to study its behavior and its geometry. So our next step then would be to study the geometric consequences of the evolution of the space-like part of the deviation vector. So we have just shown that the evolution of the space-like... Okay. Good. So now we have just shown that the evolution of the space-like part of any deviation vector is governed by some matrix. So it is natural to decompose the matrix into some irreducible components and study their geometric effect. So recall that any matrix can be decomposed into its symmetric, traceless, antisymmetric, and the trace part. So here we will do the same. We will decompose. So let's do the definition. We will decompose it into the trace part, which is expansion, symmetric traceless, which is shear, and rotation, which is the antisymmetric part. So define the expansion as B mu mu. So that's expansion. Define shear as the symmetric traceless part. And finally, define the rotation as the antisymmetric part. Good. So this is shear and this is rotation. So from all this, the matrix is reconstructed back as B mu nu equals 1/2 B mu nu theta plus omega mu eta plus shear. Good. So it is an exercise to check that theta, which we defined as B mu nu, it is also the same as B mu mu, which is the divergence of the null generator. So, as with all matrix quantities, they of course depend on the frame, and the scale invariants are those that give us the most information. So let us study the. Okay, good. Good. Okay. So as all tensorial quantities, of course, their representation depends on the choice of frame, and the scale invariants are, but the scalars are invariant with regardless of the frame, and therefore the expansion is an intrinsic quantity for a congruence. Good. So now let us study the geometric effects of all three components. So let's say we have the sigma at value lambda naught, and we have it at the value of a fine parameter along the geodesic lambda 1. So the effect of the expansion is effectively the expansion or the shrinking of the cross section of the sheaf of the geodesics. So we'll have So what is the geometric effect of the shear? Okay, let's have a similar picture. So now let's see what the shear does to the geodesics. To the special cross-section of the congruence of the geodesics. So again, we have some initial value of the fine parameter lambda naught, and we have final value lambda 1. So let's say we have such geodesics, and it will lead to the change of the relative so it will lead to relative shrinking in one direction, but expansion in the other, such that the total area is preserved. So we will have So again, while the expansion shrinks the area in total, shear expands one direction, but shrinks another one. And finally, we have the rotation, which, as you can judge from the name, would lead to rotation of the geodesics. Would lead to rotation of the tangential directions of the deviation vector of the geodesic, of the family of geodesics. So we will have and this is expansion, shear, rotation. So now this is of course a general statement where we used a generic matrix B hat, and we didn't use the properties coming from the geometry of a null hypersurface. We will now show that if the geodesic congruence contains the generator of the null hypersurface, then its rotation vanishes. And we only have expansion. We have a proposition. So if the congruence contains the generators of the null hypersurface, then its rotation vanishes. Good. So let us write down the key quantities. So we have B equals P. I'm not writing the indices here for simplicity. P is 1 plus UN plus N U. And of course it follows that U times B times U equals 0. Good. So now B hat equals P B equals P equals, well, a number of terms. So in this product, a lot of terms will vanish by the property that U times B equals B times U equals 0. So we will have that B equals B hat equals B plus U and B plus B and U plus U and B and U. Let us put down the indices. So if this mu and nu, this is mu, nu, rho, sigma, B mu nu, this is mu, rho, B nu, mu nu, rho sigma. Good. Now let us find the rotation, which is the antisymmetric combination. So we have antisymmetric combination. It is easier to find it. It is easier to wedge it, to take the exterior product of the antisymmetric part with U. So let us consider the following combination. Let us consider the U mu B hat nu rho, B hat nu rho equals of course U mu B nu rho plus, okay, so this term vanishes because we wedge U with U, this term vanishes again because we wedge u and u, and this term again vanishes. So just this. All other terms vanish. All other terms vanish. Good. So by using the definition of B, this is the same as minus u mu d nu u rho. Notice that this is actually the combination that stands in the Frobenius theorem. So if you write it on the language of differential forms, this is the same as u mu yes, and of course this is the rotation, sorry. This is of course the same as nu rho. So we have omega nu rho equals minus 1/6 u wedge du mu nu rho. Okay, checking the sign here and the factor of 1/6 here remains an exercise. Good. Yes, and of course on n we have u mu nu rho is of course 0. So u mu is of course the direction orthogonal to omega nu rho. So from wedging u mu to omega hat, we don't lose any information. So from this wedge product equals 0, it follows that the rotation itself is 0. This can be seen as follows. So if we have 0 equals nu rho equals 1/3 of nu rho plus u nu omega nu plus u rho omega mu nu, and we multiply it by n mu we then immediately get that all terms vanish except for the first one. So then we get 0 equals good. So therefore we have it. The rotation vanishes. On the null hypersurface. So now we are one step closer. Now we can use our knowledge to construct a convenient chart that describes the geometry around the null hypersurface. So later in the course we'll show that certain geometries, certain null hypersurfaces have the same features as the event horizon, and they will explicitly be linked by a result known as rigidity theorem. But this comes later in the course. So for now, let us introduce the Gaussian null coordinates chart. so Gaussian null coordinates, or GNC for brief. So this is a chart around null hypersurface, and we naturally start with considering its spatial part. So let sigma be its two-dimensional spatial cross-section. And y I runs 1 to 2 are coordinates on it. Good. So sigma is a spatial cross-section, and therefore it is a space-like hypersurface, space-like surface. That is, the tangent vectors are space-like. And the normals to sigma are two null directions, which we will use in this construction. So the coordinates. So these coordinates can be extended from sigma onto the whole null hypersurface by the parallel transport. Can be from by parallel transport. Along the null generator U. So let us write here null hypersurface with U generator. So along U mu. So it is convenient to introduce a coordinate along the flow of U mu, such that U mu is given by, such that U mu is given by d over d lambda. That is, we assign a point. We assign a point the coordinates lambda yi, the point that is parametric distance lambda away from the point of sigma. So So far, our construction is we start with the space-like surface sigma, and for any point with coordinates yi, we extend it along the flow we extend it along the flow of u. So this, of course, defines as the chart on the, this of course defines as the chart on the full null hypersurface. So this is u. So this is the point, this is then the point lambda yi, parametric distance lambda. Good. Now, yeah, so we extend it parallelly. That means that that du d over d yi on n equals duu on n equals 0. Well, this follows from u being a finely parameterized geodesic. Now we only need to extend our chart from the null hypersurface to the whole spacetime. Okay, so let us introduce the second null direction. And v mu is a second null, so v mu is a null vector field on n. We can introduce them to be, we can normalize it and put them to be in the opposite light cones. U times v equals +1. And since v is null, it naturally has v times dyi equals 0. Good. So again, it is convenient to introduce the coordinate as a affine coordinate along, as the affine coordinate, as the affine color coordinate, So again, it is convenient to introduce another coordinate as a affine parametric distance along the null geodesics generated by v. So write v equals d of dr, and we have the chart rho lambda ye, where r is the affine parameter. So if you have this point, we have the direction. We have the direction v, and we naturally have a point r, well, 0 ye, and if you had a point here, we would have the point r lambda ye. Good. So, so we can introduce the vectors u. So we can introduce the vectors u and the directions u and yi to the bulk by extending them parallelly with respect to v. So we also introduce so we also write dvu equals equals 0 everywhere. So this way we have the full chart with coordinates. Now let us just find some of the scalar products of the vectors. So from this immediately follows that u times v equals +1 everywhere, and v times t dyi equals 0 everywhere, because both are extended parallelly along v. And v is also everywhere null, of course. Now, this allows us to write the metric. So, good. So now we have found the scalar products, and now we will construct the metric. So we have found that v squared equals 0, and from this it follows that grr equals 0. Then we have found that v times u equals +1, which means that g lambda r, or better to write opposite, r lambda, equals 1. And from v times t dyi equals 0, it follows that gri equals 0. Similarly, as an exercise, check that g lambda I on n equals g lambda lambda on n equals 0. So in total, we find ourselves with the following metric: ds squared equals dr d lambda plus r some function f of all the coordinates d lambda squared plus 2r h d lambda dyi plus the metric on the space-like part, the spatial cross-section. So from this, good. So R, HI, and the HIJ are some smooth functions. So it's good. So it's good to see that all the properties, all the scalar products, we have implemented all the properties for the scalar products in this metric, as well as the properties for g lambda I and g lambda lambda, giving us the factor of R here. Sorry, because we want a metric to be at least continuously differentiable around the null hypersurface. So good. And from this, it of course follows that the metric on the null hypersurface which corresponds to R equals 0 is 2dr d lambda plus hij dyi dyj, and this bit itself is the ds squared on the spatial cross-section. So, for some geometries, which we will call the general geometries, it can happen that the scalar product G lambda lambda vanishes, not just vanishes, but its first derivative with respect to R also vanishes. So, degenerate, also known as extremal geometries, they have so the full geometry reads as ds squared equals 2dr d lambda plus r squared f tilde, which is smooth, d lambda squared plus the remaining part. So these extremal geometries will be linked to the horizons of the extremal black holes. And these geometries turn out to be quite special, and we will briefly touch some of their properties late in this course. So, to summarize, we have now just introduced a convenient chart that describes the geometry around any possible null hypersurface, which of course, which is a very important result, because of course, as we have said, late in the course, so these geometries will be linked to black hole horizons, and therefore this will describe the near horizon region of the black hole, which is of course physically very interesting. Furthermore, the extremal geometries themselves play a significant part in string theory, and in string theory as being some near-horizon limit for the branes and other string geometries. So, in total, yes. So later when discussing black holes, we will briefly return to Gaussian null coordinates. Okay. Now that we have introduced the convenient chart, we can calculate the expansion. We can explicitly calculate the expansion of the null hypersurface. So, okay. So, recall that theta equals b the trace part of b hat, also equals to b mu mu, the trace of the matrix B itself, which is b lambda lambda plus b r r plus b I, which in turn equals to, so the b lambda lambda and b r r part of course vanish, because u times b equals 0, because u times b equals 0. And we naturally have this thing equals to, by the definition of bii, to the diui, which in turn equals to plus gamma e E mu U mu. Good. So, but U is given, but what is U? U is just the d over d lambda, and therefore this thing vanishes. So U mu equals 0, 1, 0, 0, and therefore this thing vanishes. So we are left with theta equals gamma E lambda E equals to 1/2 gi mu Okay, so it is a good exercise to check that this is the same as Hij lambda, which we do, which follows directly from the metric and Gaussian null coordinates, and this is the same as d lambda of H. So, in other words, the expansion measures. In other words, the expansion measures how the spatial cross section, how the area of the spatial cross section changes with respect to the evolution. So we have that d lambda square root of H equals theta square root of H. So, in particular, if theta shrinks, then the area of the area of the spatial cross section shrinks. Okay. So, and in the next lecture, we will finally be ready to prove the Penrose singularity theorem.